So today in this video, I wanted to go over the idea of torque. So torque is, in my mind, like a rotational equivalent to force. As we start studying these rotational quantities that we are in Chapter 10, I like to sort of make a relationship to the things that we've learned before. And so for torque, I'd say it's force. It turns out that torque actually is dependent on a force, but because we're talking about rigid bodies, it's a situation where the force is applied, and instead of having an acceleration in a particular direction, like in the X or Y direction, we actually have a rotation about an axis. So in summary, we could say that a torque is a force that, when it's applied to a rigid body, causes a rotation about an axis. So we use the Greek letter tau to define torque. And it also is calculated using a cross product. It's a cross product of what we call the radius vector. Now the radius vector will go from the axis of rotation to the point where the force is acting. And so we cross that radius vector with the force. When we do that, it turns out that, of course, the torque is going to have a vector nature to it. It's not only going to have a magnitude, it will have a direction. And as we saw with many of our examples of vectors in this chapter, the direction of the torque vector is going to be along the axis of rotation, using the right-hand rule for R cross F to determine which way it's going to go. Now, the thing that I'm going to concentrate more on today in this video is the idea of finding the magnitude of the torque. So we learned about cross products in Chapter 2 when we just were learning about vectors. There were two operations we could do with vectors. We could do a dot product or a scalar product. Those are the same thing. And then we could do a cross product or a vector product. Again, those are the same things. We actually saw an application for the dot product when we learned about work. Now we're going to have our first application for the cross product with torque. In any case, we learned that the magnitude of a cross product is equal to the magnitude of the two vectors that are involved times the sine of the angle between them. So I want to take a look at this and see how we can think of this in different ways. So I drew a wrench. Here's another reminder of how well I can draw. And we're going to be loosening a nut. And of course, that's going to be the center of the nut will be our point of rotation. So I'm going to draw a force that is being applied to that wrench. And then that will allow me to draw also the radius vector. Now, if I just extend this line right here, this would be the angle between the two vectors. So, if you think about that force that's applied, I drew it at an angle on purpose because if we break it down into its components, we have this component, which would hit at a right angle, and I'm going to call this F perpendicular. And we'd also have a parallel component right here, and I'm going to call that F parallel. Now, F perpendicular is equal to F times the sine of theta, and F parallel is equal to F times the cosine of theta. You know, so when I apply a force to that wrench at that angle that I've decided it's applied at, we could also think of applying these two components at the same time. The component of the force that's perpendicular to the wrench or perpendicular to the radius vector, and also the one that's parallel. Now let's ask ourselves, which one of those is going to cause a rotation? And I think it's clear that only the perpendicular force will cause a rotation. And the parallel force, you can see that as I pull this way, that's going to do nothing to move that, to loosen that nut. Only the perpendicular component is going to do anything. And then I notice that the perpendicular component is equal to F times the sine of theta. And so I can think of this expression for torque, the magnitude, could be expressed as the magnitude of the radius vector times the perpendicular component of the force, or the force component that's perpendicular to the radius vector, because of the fact that this is just equal to F times the sine of theta. Okay, that's great. But sometimes we want a different way to figure this out. Certain geometries might make it more helpful if we can look at it a different way. So I'm going to redraw my wrench to illustrate another way to think about it. And I'm going to still have my force at just some angle. So this is the force that I am applying. And then this would be the radius vector. And then, of course, this is the angle between the two vectors. Now, there's another way to think about how I can calculate the magnitude of this torque, and it's called using either a lever arm, or sometimes it's called the moment arm, or as we see in our book, we're going to call it R perpendicular. And so what we're going to do, in a sense, is now, what if we coupled the radius with the sine of theta instead of putting the sine of theta with the force? Notice when we put the sine of theta with the force, that gave us the force that was perpendicular to the radius vector. But what if I find the distance, the radius vector that's perpendicular to the force itself? And that's what we call these three different names. You might see them used depending on the source that you look at. So it could be known as the lever arm or the moment arm or R perpendicular. So in order to do this, the first thing we have to do sometimes is we have to extend the line along which the force is acting, and this is what we call the line of action of the force. The idea being that that force is working along that line, or is being exerted along that line. And the reason that we're just extending it is because what we want to do is we want to find the distance from the axis of rotation to the line of action. Now, essentially what we're finding is the distance between a point and a line. And you might know or remember from calculus or math class that in order to find the proper distance from a point to a line, that measurement has to hit the line at a right angle. And so if we thought about going to this line and hitting it at a right angle, this is what we're going to call R perpendicular. And so if we start thinking about it, now we can see, okay, now right here is the angle between the radius vector and the force, and we call that angle theta, but notice that this is theta as well. And that calculating R perpendicular we could do using our trig would just be equal to R times the sine of theta. And so another way that we can express this torque expression is as R perpendicular times force. And so it's two different ways to interpret this general expression of how we calculate the magnitude of a cross product. And so I wanted to show you how we interpret both of those. It honestly will depend on the individual situation. Sometimes it's very easy to see this application where I can just find the force that's perpendicular to the radius. And other times, honestly, it's easier to find this perpendicular distance and just multiply it by the force. In the end, we'll still get the same value for the torque. I'm also going to ask you to review, because of the fact that torque is a cross product, to review how you can calculate the cross product of two vectors if they're written in unit vector form. I made a video about that early in the semester, I'm going to ask you to review that so that you're up to speed on how to do that. All right, see you in class.